All right, welcome back, everyone. Ready for another deep dive? Today, we're tackling a pretty ambitious goal in AI video generation. Longer, more coherent narratives. Those compelling multi-scene stories that actually keep us hooked for a whole minute.
Yeah, a minute might not sound like much, but when you look at what current video generation APIs can do, it's a pretty big leap.
Think about it. Sora maxes out at around 20 seconds, MovieGen at 16, you've got Luma hitting 10. Even VO2, which is pretty cutting edge, is still capped at 8 seconds.
And that's for relatively simple scenes. When you start thinking about multiple locations, character interactions, or real plot unfolding, it gets incredibly complex.
Exactly. And that's where this paper, 1 minute video generation with test time training, comes in. This team from NVIDIA, Stanford, a bunch of the UCs, they really pushed the boundaries here.
And they didn't just go for longer videos for the sake of it. They focused on narrative complexity.
Right. For those of you who want to check out the paper and the results, by the way, you can find it all at test-time-training.github.io video-dip. They've got the code, some fascinating video examples, the whole shebang.
Definitely worth a look. But for our deep dive today, let's unpack the core innovation. These so-called test time training layers, or TTT layers for short.
These are the key to how they're tackling that long context problem, because generating even a single minute of video, that can easily involve over 300,000 tokens.
Yeah, and with traditional self-attention, which has that quadratic cost, processing sequences that long becomes incredibly demanding. Just not really feasible.
So to make things concrete, they've used a super interesting data set as their proving ground. Classic Tom and Jerry cartoons.
Now, before anyone thinks they're just aiming for photorealistic cat and mouse chases, the goal here was really about pushing the limits of storytelling.
It's about those complex narratives, the dynamic motion, the exaggerated action, and keeping everything consistent over a longer time frame.
Things that you just don't see in those shorter video clips most models generate. So even though it's animation, the core challenges of narrative generation at that scale, they're absolutely relevant to pushing the boundaries of AI video overall.
Okay, so let's dive into the heart of it. These TTT layers, what are they all about?
Well, first, we need to understand why standard recurrent neural networks, RNNs for short, have such a hard time with really long sequences.
Because it all comes down to their fixed size hidden state, right? Their memory, so to speak.
Exactly. And even with newer, more efficient mechanisms like Mamba or DeltaNet, which use a matrix for that hidden state, the problem persists. They just can't retain enough information about those long-range relationships between tokens when the sequence gets really long.
It's like trying to remember the plot of an entire novel using a single sticky note.
Right. You're going to miss a lot of crucial details, those connections between characters, the nuances of the plot. So how did TTT layers get around this? They do something really clever.
Do tell.
Instead of having a static hidden state, they use something much more dynamic. The hidden state itself is a small, trainable neural network.
Wait, so the memory itself can learn and adapt?
Precisely. In this paper, they used a two-layer multi-layer perceptron, or MLP, as their hidden state. It's got GELU activation, layer normalization, even a residual connection. So it's not a fixed matrix, it's a mini neural network whose weights can actually be updated as it processes the sequence.
So it's not just storing information, it's actually learning and refining its representation of the video as it goes. How does that work in practice?
It's all in the update rule. At each time step, when the TTT layer gets a new input token, it doesn't just update a static vector or matrix. It actually does a gradient descent step to adjust the weights of its internal MLP. Those weights are represented by W subscript T in the paper.
So it's like a tiny optimization loop happening within each TTT layer.
Exactly. And this update is driven by a self-supervised loss. It's denoted as that cursive L in the paper. You've also got the current input token, X subscript T, and a learning rate, eta. So the hidden state at time T, W subscript T, is basically derived from the previous state, W subscript T minus 1, by taking a step that minimizes this loss function.
Okay, I think I'm following. And the output from this TTT layer is then just whatever this updated MLP produces.
Right. The output Z subscript T is the prediction generated by the MLP with these newly refined weights. And that's why it's called test time training. Because even when you're just generating video, even during inference, you still have this mini training loop happening within each TTT layer.
That's pretty mind-blowing. It's like the model is constantly learning and adapting its memory as it's working, And it's all self-supervised, so you don't need explicit labels for this inner training loop?
Exactly.
Oh.
And the self-supervised task they designed is super clever too. It's not just about reconstructing the original input. They use these learnable low-rank projections.
Rejection.
Yeah. So think of it this way. You've got the input, X subscript T. They apply a projection matrix, theta subscript K, to it. This kind of corrupts the input a little bit. Then you've got another projection, theta subscript V, that produces a target. And the goal of the MLP, with weights W, is to try and reconstruct that target from the corrupted input.
Okay, so it's like a denoising task, but with these learnable projections to make things more challenging.
Exactly. And the output rule is modified slightly too. You apply another projection, theta subscript Q, to the input before feeding it to the MLP. These thetas, they're all learnable parameters that are optimized in the outer training loop, just like the rest of the network.
So it's kind of like the key, value, and query matrices in self-attention.
Right, they play a similar role. So you've got this inner loop where the MLP's weights are being constantly adapted, learning how to represent the video sequence. And then you've got the outer loop where the network as a whole, including all these TTT layers and their projection parameters, is trained on this massive Tom and Jerry dataset.
It's meta-learning, right? The outer loop is teaching the inner loop how to learn effectively.
Exactly. It's pretty elegant, isn't it? Now, how do you actually integrate all this into a full video generation model?
Right, because they didn't start from scratch. They used a pre-trained diffusion transformer, CogVideo X5B.
Great model. But as we said, limited in terms of temporal scope, it could generate maybe 3-second clips.
So the challenge was to supercharge that temporal reach.
And they did that by adding TTT layers, specifically their TTT MLP variant. They put these layers after each self-attention layer in the transformer blocks.
So they're augmenting the existing architecture with these new memory mechanisms.
Exactly. But they also added something crucial. Learnable gates.
Gates. Why gates?
Stability. You're introducing these new TTT layers with their own weights into a massive pre-trained network. You don't want to just shock the system.
Makes sense.
The gate basically controls how much influence the TTT layer's output has. Mathematically, it's defined as ton of alpha, which is a learnable vector, times the TTT output, plus the original input X.
And alpha starts out close to 0, so the TTT output has a minimal impact at the beginning.
Right. And as the TTT layers learn, as they become more adept at handling long-range dependencies, the gate can open up, allowing their influence to grow. It's a smooth integration process.
Pretty clever. Now, diffusion models are non-causal, right? Meaning they consider the whole sequence when generating each frame. So how do they handle that with the TTT layers?
Good point. They introduce bi-directional TTT layers. Basically, take the input, reverse it, pass it through a regular TTT layer, and then reverse the output again.
So the TTT layer gets to see the sequence both forwards and backwards in time?
Exactly. So their modified transformer block actually has 2 gated TTT layers, a forward one and a bi-directional one. This allows the model to capture dependencies from both the past and future contexts.
Okay, so we've got the architecture, we've got the data. How does the whole pipeline come together to actually generate a minute-long video from a text prompt?
First, they segment the input videos into scenes, and then each scene into those 3-second chunks. Then, the text prompt, which they call a storyboard, and it's in a specific format they define called Format 3, that gets tokenized.
Format 3.
Yeah, it's got keywords for scene starts and ends. It's pretty detailed. Anyway, those text tokens are interleaved with the video tokens for each 3-second segment. And then the whole thing gets fed into the model.
And to keep the computational costs manageable, especially with self-attention.
Right. The self-attention operates locally within those 3-second segments. So it's not crunching the entire minute-long sequence at once.
That makes sense.
But the TTT layers, they operate globally.
Yeah.
Because they have linear complexity. They can efficiently process the entire concatenated sequence, all those 3-second segments together.
So the TTT layers are responsible for maintaining that overall coherence across the entire minute.
Precisely. Now, how do you train this beast? They use a multi-stage context extension fine-tuning strategy. They start by fine-tuning the entire pre-trained CogVideo X model on those 3-second segments.
Okay, starting small.
Exactly. And initially, the TTT parameters, those gate parameters, they get a higher learning rate compared to the rest of the network.
So they learn faster at the beginning.
Right. Then over 4 stages, they progressively increase the segment length. 9 seconds, 18 seconds, 30 seconds, all the way up to 63 seconds.
It's like gradually stretching the model's temporal muscles.
Great analogy. And to avoid catastrophic forgetting, to preserve that pre-trained knowledge, they use lower learning rates for the TTT layers, the gates, and even the self-attention layers in those later stages.
So the new components learn quickly at first, but then they settle down, allowing the pre-trained knowledge to shine through.
Exactly. It's a delicate balancing act. Now let's talk about this Tom and Jerry dataset. 7 hours of classic cartoons. That's a lot of data.
And annotating all that, breaking it down into scenes, segments, writing descriptions.
It was a huge effort. They used 81 episodes from 1940 to 1948, all super resolved to 720 by 480. The annotations were super detailed too. Each 3-second segment has a whole paragraph describing it. Not just what you see, but the context, the actions, the camera movements.
So these aren't just simple captions. It's a rich narrative data set that the model can really learn from. Now, given those long sequences and that inner training loop in the TTT layers, how did they parallelize the training?
They use inner loop many batches. So instead of updating the hidden state for each token sequentially, they process a small batch of, let's say, 64 tokens at a time, calculate the gradients, update the weights, and then generate the outputs for that entire batch.
So it's bringing mini-batch training to the inner loop.
Exactly. And they also did some clever optimizations to leverage the tensor parallelism on NVIDIA GPUs. They distributed the MLP weights across the streaming multiprocessors, used DSMEM for efficient all-reduce operations, all to minimize those costly transfers between the HBM and SEP.
Getting into the nitty-gritty there. So they've got the architecture, the data, the training, the optimizations. How does it all perform?
That's the million-dollar question. They did a human evaluation, which is really the gold standard for this kind of generative task.
Because ultimately it's about how humans perceive the quality of the generated videos.
Exactly. They used the MovieGen benchmark, focusing on 4 key aspects: text following, motion naturalness, aesthetics, and temporal consistency.
How do they measure those?
Pairwise preference blind comparisons. You get 2 videos generated from the same prompt by different methods. You don't know which is which. You pick which one is better based on one of those 4 criteria.
So it's all about relative comparisons, no absolute scores.
Right. And they did this with 100 generated videos per method across a variety of plots using a diverse group of evaluators.
And the main result? How did TTT MLP stack up against the competition?
It crushed it. An average of 34 ELO points ahead of the baselines.
34 ELO points, that's significant, right?
It is. The paper compares it to the difference you see between top-tier language models, like GPT-4 versus GPT-4o. And it's worth noting that simple approaches like local attention or a linear hidden state didn't even make it past the preliminary rounds.
So they couldn't handle those longer sequences.
Exactly. Now, where did TTT MLP really shine? The biggest improvements were in temporal consistency, with a 38 ELO point difference, and motion smoothness, with a 39-point difference.
So smooth, coherent videos that stick to the story.
Precisely. And if you look at Figure 5 in the paper, the visual comparisons are really striking. TTT MLP maintains scene consistency beautifully, preserves details across transitions, generates much more natural motion. The baselines, they have weird artifacts, environments changing randomly, inconsistent character appearances, duplicated actions.
It's those little inconsistencies that really break the immersion.
Exactly. Now, of course, TTT MLP isn't perfect. It's actually not as good as some of the baselines on those shorter 18-second clips.
So there might be a trade-off there.
Potentially. And computationally, it's still more expensive than gated DeltaNet or Mamba 2, both for training and inference. They have a nice latency breakdown in Figure 6.
Okay, so there's room for improvement there.
Yeah.
And they mentioned some visual artifacts still present in the generated videos.
Right. Things like object morphing, unnatural floating, inconsistent lighting. They think some of that might be limitations of the pre-trained CogVideo X model itself.
So the backbone model might be holding things back a bit.
Maybe. But overall, TTT layers, particularly TTT MLP, are a huge step forward. They show that you can generate much longer, more narratively complex videos with AI and do it within a diffusion transformer framework.
And they outline some exciting future directions too, right?
Yeah. Faster implementations of TTT MLP, exploring different integration strategies, different backbone models. And they even talked about scaling up TTT layers themselves, maybe using transformers as the hidden state.
Wow, a transformer as memory. That's wild. Okay, as we wrap up, what's one thought-provoking question you'd leave our listeners with?
Well, if you think about it, these TTT layers prove that you can make a hidden state much more expressive, much better at handling long-range dependencies by making it a neural network. So what other parts of our sequence models could we upgrade in a similar way? What if we made more things meta-learnable, adaptable at test time? What kind of crazy capabilities would that unlock, not just in video generation, but in AI as a whole?
That's a great question to ponder. Thanks for joining us for this deep dive. We covered a lot of ground, but this is a paper worth digging into. Check out the full paper, the project website, all those awesome video samples. And until next time, keep exploring the frontiers of AI.